This is Albert. He's the 3D printed evolution of my PVC robot dog, and he's officially taken over my desk. Browsing the internet, you'll see commercial robot dogs costing anywhere from hundreds to thousands of dollars. But Albert costs less than $50 to build, and I am completely open sourcing this entire project. I'm sharing the STL files, however, if you don't have a 3D printer yet, go check out my previous video where I show you how to build the chassis out of simple PVC sheets. Everything you see, the STLs, the wiring diagrams, and the modular code, is live on my GitHub page right now. In my previous video, we built the body. Today, we're giving him a brain. I'm breaking down how to create complex behaviors, and I'm going to show you how LLMs like ChatGPT, Claude, and Gemini are changing the way we do robotics forever. And finally, wait till the end for some tips on powering Albert properly. I had a lot of issues making him battery-powered, and I want to share exactly what I learned, so you don't make the same mistakes. To bring Albert to life, the first step is defining what I call Gait primitives. Instead of using inverse kinematics, I'm using simple cosine functions. I use a standard cosine for the upper leg to handle the forward swing, and a rectified cosine for the lower leg. By cutting that lower wave so it never goes negative, I can mimic a cycloid pattern. This ensures the foot lifts high enough to clear the ground and then glides forward. To steer, I'm using amplitude modulation. To turn left, the code simply increases the movement amplitude on the right side. Now we can proceed by defining a motion logic. This part I did using Claude, which saved me an incredible amount of time. I simply inserted my primitives into the prompt and asked it to follow some specific logic. For example, look around with the neck, and when you see something closer than 30 centimeters, go in that direction. Similarly, for the autonomous exploration mode, I asked Claude to follow this logic. Go forward, and when you see an obstacle, look right. If it's free, go there. Otherwise, look left. And if both sides are blocked, simply go backward. Now, let's talk power. Originally, I looked into a standard LiPo setup, a high discharge battery, a charging module, and a step-up converter to get a stable 5 volts. But that stuff adds up fast. It was going to double the cost of the robot. So I decided to hack the system. I bought a basic $5 power bank and decided to take it apart. Inside, you find exactly what you need: a high-quality lithium cell and a pre-made circuit that handles charging, protection, and a rock-solid 5-volt output. But even with the power bank, I ran into a major wall. During testing, the legs were incredibly unstable, twitching and causing the ESP32 to reset every time Albert tried to take a step. At first, I thought it was my code, but then I realized the problem was hardware interference. The servos and the ESP32 were sharing the same power line. When the 8 servos kicked in, they created a massive voltage drop and electrical noise that choked the microcontroller. The fix? I leveraged the power bank's dual output design. I ran one dedicated line to the servos and a completely separate one to the ESP32. Instant stability. Albert is a testament to what you can do with a $50 budget, some 3D printed parts, and the help of AI to bridge the math gap. He's my new favorite desk companion, and he's ready for you to build him. If you enjoyed this deep dive into the brain of Albert, hit that subscribe button. Let me know in the comments what behavior I should teach him next. Thanks for watching, and I'll see you in the next one.